Welcome. Thanks for coming in such big numbers. I'm scared. So my name is FX or Felix, whatever you like more, and I'm going to talk about router exploitation today. Awesome. I'm not seeing my slides. So this is what I'm talking about today. So first, a quick introduction. Then we're talking about like the general class of what vulnerabilities do we actually have in routers? Like what is actually worth attacking? We talk a little bit about architectural considerations, like what is significantly different from your Windows box to a Cisco router. And then I'm going to spend quite a lot of time on a very simple question, which is the return address. If you override it, what is it going to be? And we're closing out with shellcodes for routers, and for those corporate and service provider guys among you, we're talking about protecting routers as well. In addition, there is what I call the Blackhead Ometer. It essentially splits white hats and black hats into the same scale as acid and base. So on the top it's white hats, and on the bottom it's black hats. So let's say if you're a corporate suit and tie guy, then just ignore everything, every slide that is not in the top level. If you have a CISSP, you can go as much as like to the middle. And if you're really interested into assembly and hex code, then you can go all the way down to the dark side. So, exploitation of router vulnerabilities has been shown to pretty much no end. I mean, like, I'm talking about that topic for almost 10 years now. And I'm really happy that you guys don't, like, get bored of it. The problem, or the interesting thing is, there haven't been any noticeable large-scale incidents that people would actually have seen on the internet. Like, there hasn't been a service provider whose entire router network got owned entirely and shut down or modified. At least we didn't notice. And we developed tools to find exploited routers and backdoored routers, and the experience shows that there is actually not so much ownage going on in the real world, that up front. So it really doesn't happen in a large scale so far. All the known incidents that were published were configuration issues, insider attacks, like I think it was the city of Chicago where someone like changed all the configurations and like held the routers hostage, or very trivially exploited vulnerabilities, like very, very simple stuff like the HTTP vulnerability on Cisco. So this is extremely interesting because, of course, it's a high-value target, but we're not seeing large-scale advanced exploitation, and this is what this talk is about. So what's the motivation behind it? Everything, like really everything that's remotely even handling data that an attacker could be influencing or providing is exploited to no end. Like, if you're reading full disclosure, if you're following vulnerabilities, there are vulnerabilities published for software that you potentially have on your PC, but you often never even hear that it exists. So why don't we see large-scale exploitation of Cisco routers, or why don't we see Metasploit modules that attack Cisco? I think it's well established that infrastructure is actually what attackers really want to be in, because that gives them the most power. So what is the problem? There's obviously a couple of obstacles that make it a lot harder to write decent exploits for Cisco routers than for Windows, Linux, Solaris, HPX, whatever. And knowing what the difference is will actually tell you when those obstacles are overcome. Someone at some point in time is going to have the right idea. And if you see an email on a public mailing list saying, look, I found a way to determine a solid return address on Cisco routers, you should actually know what that means. You should actually know that this means you call your networking guys and tell them to power off, like everything, right now, and not ask questions. So this is what this talk is about. What obstacles do we have and what you should watch out for? If it happens, you're doomed. So, vulnerabilities in routers. Let's say we want to exploit a Cisco router. What do we need? We need something that we can attack, right? So, when you actually look, there is comparably little research in the topic by itself. So we have like 14 vulnerabilities published for Cisco iOS in last year. Juniper actually doesn't report anything. They say, well, we have occasionally this problem here with OpenSSL, blah, blah, but they're not actually saying, well, we tested our BGP daemon and we found this and that vulnerability in there. The only thing you even find on their own software that you can blame on them is they had a memory leak with IPv6 in kernel. Not a big deal. Other router vendors actually don't publish anything about vulnerabilities in their equipment. Vulnerabilities in networking equipment actually get fixed a lot of time as functional issues, because essentially this equipment sits there in this network all day long and is receiving packets. And one of those packets is going to kill the box. The regular network engineer is not even thinking about this as a security issue. What he's thinking is like, damn, the box crashed. What am I going to do? Send in a bug report. Okay, fine. And then someone at Cisco or Juniper or whatever is going to go and say, yeah, well, here's this packet that crashes the router. Let's go fix it. So they're not even noticing vulnerabilities as such in their systems. Therefore, the information going out to the customer is pretty much the same. We have this minor update here, and it's going to fix a rare crash in the system. So what could that be? There are essentially three classes. The first one is service vulnerabilities. Basically, services are everything that is like opening a TCP or UDP port or like handling some specific type of network traffic. Services are on routers as well. So you do have administration interfaces, Telnet, SSH. You do have SNMP, of course, because that's like how everything is managed. And this is why we all love this SNMP bug from last year so much, because it pretty much affected anyone and everyone. And you have some people are running interesting services on their routers, like TFTP servers, FTP servers, HTTP servers for configuration. But seriously, if your network administrator has as much clue as, let's say, a wet piece of toast, he's not going to run web servers on his routers. So this is maybe of interest for small companies that have no network people at all. But for real networks, for service provider networks, services like an HTTP service on a router are not of any interest. Pretty much every implementation of services of that kind on routers had vulnerabilities in the past. I mean, the vulnerabilities found by the IRM guys on the Cisco FTP were so bad that Cisco's fix was, we're going to remove the FTP server entirely and going to replace it sometimes in the future when we know how to code this. This pretty much tells you the state of code quality we're talking here, right? Other than that, routers actually don't expose that much functionality to the attacker. So routing protocols, which is like the router's core business, run pretty much internally. Like they're not announced to the internet. Enhanced IGP, OSPF, they require you to be in the same multicast domain. That is obviously not the case if you're coming from the internet from a different country and trying to attack this infrastructure. So this is not really an option. RIP is so damn simple that even Cisco can't fuck it up. So there isn't anything to exploit. BGP is a very good example. It's a global routing protocol, but it requires you to say explicitly, this IP address is my peer, and I'm going to talk to this IP address. So unless you are this IP address, in which case you can do a lot other shit, you're not going to send any traffic to this router that is going to disrupt him. So that's not a very good attack vector. There are layer 2 protocols like DTP, VTP, CDP, whatever. They require local link access, as in you have the same cable. So this is not really useful if you're sitting in China and you want to take over someone else's infrastructure. And some routing protocols like ISIS don't even speak IP. Like they're ISO protocols, they're not IP. So you're not going to route them over the internet. If you are sitting in the same multicast domain as a router, that router has a very bad time. So within corporations, within multicast domains, router exploitation is significantly easier than over the internet. So the threat is actually more from people sitting in your network than people sitting outside of the network. But in the internet, simple internet engineering rules say do not accept routing updates and routing information from arbitrary people, because then everyone with a DSL or even ISDN line will say, well, okay, I know where 10.0.0.0/8 is. And yeah, your routing would be toast. There is one notable exception to that. Excuse me. And this is the IP options vulnerability. So essentially, it's triggered by 4 different protocols. Some of them most have never heard, like the URL rendezvous directory protocol. Like, raise your hand if you ever used that. Yeah, see, same here. But there is one protocol that is occasionally used. It's called Icmp. And it's occasionally used to actually ping routers, right? And this is where the vulnerability is triggered. It's actually really interesting. It parses the IP options in an IPv4 packet, and instead of like stopping when it sees an end of option flag, it will actually keep parsing it and looking for a loose or strict source route. And then because it's a ping, they try to be clever and went like, let's say, okay, we got pinged and it was source routed, so we want to respond the same way back. So we need to turn around the source route, which we do in a fixed sized buffer of 8 times 4 byte. And if we have more than that in this packet, we get owned. It's a stack-based buffer overflow. So it's an ideal research vulnerability, because it's exactly what every attacker wants to have. It's like you send a single ping packet to a router, you get a stack overflow. What are you going to do with that now? And this is essentially what we're talking about later. However, people in the industry are working really hard to change that landscape and to make router exploitation a lot easier. They're deploying IPv6, which all by itself is, let's say, new, and new stuff tends to be broken. But it's relatively hard to fuck up v6. So because of that, they're also deploying VoIP. Because that has everything you want. It has variable length integers. It has ASN1 encoding. It has standards the size of a, of a bar share printed out. It has HTTP-like behavior with zip. It has pretty much everything you want from an attacker point of view. And then we have the governments that chip in and say, well, but this is not easy enough yet, so let's deploy lawful interception on all the internet backbones. So we actually do have remotely managed sniffing and traffic interception functionality within all the routers, implemented in a way so that no network operator is going to see it. Thank you. We also get stuff like Ssl Vpn. Cisco has new pieces that do web service routing, as in like they're making routing decisions based on XML files flying through the router. And they even went ahead and implemented a web service management agent, which is a remote management interface to your Cisco router driven by XML over HTTP. Well, nice. So other vendors don't want to stand behind. So Huawei, Quidway, access level routers come by default enabled with all the VoIP H323 services. Like you have to explicitly turn them off. But the good thing is network engineers are a really old school bunch. They don't really like to run that crap on their routers. So adoption is really slow. The only thing that pushes them is, well, management saying that they want voice over IP. And then we have something like client-side vulnerabilities. Client-side vulnerabilities are the big thing in personal computing for a couple of years now, pretty much since the introduction of XP SP2 and the personal firewall on every single Windows machine. Everyone is focusing on client-side vulnerabilities, which is, well, understandable. Routers are really, really bad targets for client-side vulnerabilities because routers are essentially never clients. Nobody uses a router to surf the web. Nobody uses a router to watch porn. Unless you have an libAA streaming so you can watch porn in ASCII, but then it's still going to be slow. So there are just very few cases in which routers are actually clients, which is authentication services like Radius and TechX, name resolution, sometimes inadvertently. Like if you don't tell a Cisco router that it doesn't have a name server, and you type something on the command line that is not recognized as a command, as in like you just fat finger something, it's going to broadcast, like literally broadcast a DNS request. Anyone who answers is going to be the one answering correctly. And your router is going to try to connect to whatever that IP then said. So other than that, routers are really not really good clients. This might change with VoIP and HTTP services, but other than that, client-side exploitation on routers really doesn't play a role yet. And then there is what I call the transit vulnerabilities. Now imagine this, just like, okay, let's do a hacker dream here for 2 minutes. So you have a vulnerability that is triggered after forwarding a packet by forwarding a packet. Wouldn't that be cool? So it forwards the packet and then it dies on it. That would be really interesting because you can send a packet across the internet and then like everything in the path either dies or is not vulnerable. That would be really nice. This is what I call a transit vulnerability. It's highly unlikely because routers really try really hard to not look at the packet. Like they really don't want to look at the packet because that takes time, that takes CPU cycles. They want to take the packet and fire it out an interface as fast as they can. So some traffic is actually inspected on every hop. IPv6 comes to mind because IPv6 has hop-by-hop headers, which, you know, by the name say you have to take this packet, you have to look at it, you have to parse it, potentially do something with it, which is when stuff goes wrong, right? And other things like source routed packets, but nobody allows source routing on the internet, at least on the IPv4 internet. So far, we haven't seen a single transit vulnerability. It hasn't happened yet. So, now we know what vulnerability ways we potentially had, so what about the architectures? Here's a little comparison, the way I see the routing world. So, you take Cisco iOS. It's a monolithic ELF file. We're talking a lot more about that. Default behavior, like if something goes wrong in the machine, is to crash the device, to reboot the entire machine. Therefore, and we're going to go way more into detail here, exploitation is really hard. Now you take a service module. You take a line card for like 65 series switch or 72 series router. Well, those line cards actually run Linux. And they actually run a really old kernel. So their default behavior is the process crashes and is potentially restarted. Therefore, exploitation is what? Pretty much like exploiting any Linux machine in the 90s? Yep, that's what it is. Juniper, Junos, is a no more free FreeBSD. So they took FreeBSD and jailed it. Internal joke, sorry. And put it onto a router. And well, their default behavior is a process crash. So if you try to exploit a Juniper machine, you're way better off than trying to exploit a Cisco machine. Huawei actually runs two different ways. Their VRP either is VxWorks or Linux. Both have pretty much the same behavior, except for Huawei opted for device crash as fault behavior in the VxWorks. But it's actually really doable. And your arbitrary plastic, like DSL router, $10 at Fry's, is Linux-based and is pretty much like owning a regular Linux machine. So, the easy ones. Essentially, if you have virtual address spaces, you have processes, and you have UID 0, you're talking Unix, and how to exploit Unix, everyone knows that. So this is actually not a big deal. There is very little we can do in terms of detection or in terms of prediction to say when large-scale Juniper ownage is going to happen, except for the fact that we don't actually have many services that are exposed to the internet. See a couple of slides before. And then there's the hard one. The hard one is the one mostly shipped around the world, and it's iOS. And iOS is a single large fucking ELF binary. It's the largest Hello World program you've ever seen, all in one thing. It has a shared memory architecture. It has virtual memory mapping according to the ELF header. So it has a text section and a data section and a BSS section, and that's about it. And it runs right on the CPU in supervisor mode. There is no protection whatsoever. It has one shared heap, like everything shares one single heap, which is essentially just a fat double linked list. All the processes are actually threads, so because they have no memory separation whatsoever, they're little more than a CPU context and a like VTY assigned to them. And they have a run to completion scheduler. Remember Windows 95? This computer is not responding anymore. This is how Cisco works. So the consequences is Cisco can't recover from any fault within their software. If they detect memory corruption, if they detect anything not working in their software, they have to crash the device, pretty much like Windows 95. They cannot recover from corruptions in the heap because they have one. If that is corrupted, they need to reboot. They have integrity checks going over the heap all the time, making sure that it's not corrupt, because if it's corrupt, stuff is really gonna break. And they can't recover from CPU hogs. If one process doesn't pass execution back to the scheduler, then the machine needs to be killed because, well, they don't know what the process is doing and they can't kill the process. Remember Windows 95? Yeah. So the memory layout is, as I said, based on the ELF header. So what you have is a couple of addresses for different things. And so the initial address for the ELF file is static, but that's about it. Because then you get all the dependencies, because the size of one section essentially tells you where the next section starts, as with every program on a Unix machine. It's an ELF file. And we have a couple of different iOS images. So every iOS image is built from the scratch. And up until now, or up until a couple of years back, it looks like every single engineer at Cisco had his own makefile for iOS. No, I'm not kidding. When you boot a Cisco machine, it actually tells you the username, the corporate username of the guy who compiled it, for a very good reason. Like, where's Travis's makefile? The contents of what you actually get in a Cisco iOS image are dependent from the makefile, from the platform, major and minor version, kind of makes sense, release version, kind of makes sense, release train, very interesting concept. So essentially you could imagine this like you're running Windows 2000, and if you run the T train, you're actually getting Solitaire from Windows XP. So you have the technology advanced train, right? You get a couple of modules from the next version. So we have different trains. Then we have different feature sets, because this is how they bill for the iOS images. And we have special builds. Like, most of the large service providers are trying really hard to get away from the special builds, but everyone used to have their own. Like, there was a special build, 12.2 something T-Mobile, 12.2 something Verizon, 12.2 something, you know. So asking Cisco's feature navigator on the number of images, you're actually getting the number 272,000 images. Supported software versions, different. See how that is difficult for exploitation? Theoretically, that means you have as many memory possible layouts on the remote machine when you're trying to exploit it. Which means you have a chance of 0.000366% of guessing the right address. This is very bad. Assumptions about where your heap is, so you could heap spray the machine and jump into it, for example, are really bad because they're based on the image, so they're based on the same number. And assumptions about where the stack is, because you have a stack overflow and you think, well, yep, LF1, right, I overwrite the return address and jump back into the stack. Well, the stacks are blocks in the heap. So essentially you have the same chance all over again. This means Cisco's entirely and epically fucked up build process is a better protection than any ASLR that you've ever deployed. They have, by factors, more entropy in the address space than any other protection mechanism I've seen. So this is not only a problem for the return address, this is also a problem for the shellcode. Like, this whole beast is compiled at once. Therefore, they don't need any central registry on where functions are. You know, the reason why you can write such a cool Windows shellcode by parsing kernel 32 and then looking for the export section and looking for a load library and get proc address is because it's modular, because kernel 32.dll needs to tell everyone else where the functions are. Well, in iOS, it's all compiled in one beast, so they don't need to tell anyone where the functions are, which means your shellcode is not going to know. That is bad. The image doesn't contain any hints on where stuff is. And there's no guarantee that data structures are going to be the same between versions. In fact, there is actually a guarantee that data structures are not going to be the same between versions, because Cisco iOS engineers love to add a non-used field into centrally used structures in their code just for the fuck of it. The next version, they're going to take it out again. So the use of platform code, this is what shellcode actually does. You know, shellcode is actually just a little trampoline that calls code on the attacked platform to spawn a shell. You know how big shellcode on Unix would be if you had to implement a listener, a shell, and a telnet daemon all in your shellcode? You would upload megabytes until you actually get your remote root shell. So this was actually really hard on iOS. Which brings us to the return address dilemma. Where to return to? The stack, we talked about the stack, it's somewhere in the heap. It's entirely unpredictable. iOS code, well, the location depends on the image, right? And we have a couple of those images, so guessing those would be bad. We would need to know the image version, which we don't. And we would actually need to have a copy of that particular version to disassemble and know where the addresses of the functions are, which we don't, because if it's a special build for a service provider, we're not going to have that image. Well, then there's the data section and the read-only data section and all that, but their location actually depends on the image and on the code section and how much code was compiled into the section. I took a couple of thousand images that I happen to have laying around, and compared the addresses of their sections, and only 24 out of those 1,597 images had one single section with a common starting address. That doesn't even mean it contains the same stuff in the same order. So sections are not really a good return address thingy. However, in 12.4, it looks like Cisco started to align sections, which is going to be interesting. If they keep doing that, they might actually ruin their inadvertent ASLR feature. Well, then there's this great idea you could jump into I/O mem. I/O memory is on shared memory routers, like on the smaller ones. It's the area where they manage all the packets in. So at one point I figured I should actually just jump into I/O memory, and I built a valid IPv4 packet that is also executable code, which was a nice exercise until I realized I/O memory is not executable. Heap spraying is not an option either, because you have very, very little, as in almost none, control over the machine. Heap spraying is nice if you're exploiting a browser where you provide all the data. It doesn't work on Cisco's. You're not controlling the heap, period. And partial overrides would be an option, right? You just override like the last octet of the return address, and then you jump slightly into your stack or something. Well, that would be nice if we were not running on big endian machines, in which partial overrides means we're essentially changing the entire area of memory we're looking at and just crash the device. So this is not an option either. The current best bet is something called Ramon. Ramon is the bootloader of Cisco iOS. It's essentially their boot up BIOS. It's mapped initially into memory. It's used to boot the machine. It provides some basic functionality, and it's mapped at fixed addresses, and it's that code. Like when iOS runs, Ramon is no longer used. So Ramon is actually mapped on a stable address based on the line of Cisco routers you're talking. Excuse me. So for 2600 and 1700, it's actually on the same address. And as you see, for the 36 series, it's on the same address too. So you reduce the amount of information you need down to how big is the fucking box I'm trying to exploit. The version distribution is obviously a lot smaller because, first of all, who updates a router BIOS? Essentially nobody. So it depends on when the box was actually sold, which is good because Cisco loves bulk sales. Cisco is a sales-driven company, so they go into a customer and say, we're going to sell you new boxes for your entire network. Great. It's going to be all the same Ramon version because they're all shipped at the same date, pretty much. So this is good. If you Google around and you see the left Pac-Man, this is pretty much like the version distribution for 26 series routers. So you see the initial version, the oldest version, is this big fat piece of the slice. And on the right you see a regular real-world network with about 500, over 500 devices. And this is over all different machines they have, like from the smallest to the biggest router. This is the ROM-on version distribution. So for a single chassis type, they usually have one ROM-on version. So how do we misuse ROM-on? We use return-oriented programming. Who has seen the talk on return-oriented programming last year? So few people, you go to the wrong talks. This was awesome. So you should really check out the slides. Essentially what you do is you take existing functionality in code. You take the tail of functions, because the tail of functions always does the same thing, like restore registers, adjust stack, return, right? So you take that, and then you look, what's the last instruction before that? Is it an add? Is it a memory write? Is it something, something fine granular? Because if it adjusts the stacks and then returns, you control it. And so you can chain this together and build functionality based on function tails. So the idea was to use that on ROM-on, and it actually works nicely. Okay, I'm not seeing shit here, great. So this is how it works. So you have your regular stack-based buffer overflow. This is PowerPC code. So you have the buffer overflow happening, so you're writing stuff onto the stack, right? You see where saved SP and saved LR was. This is where the saved stack pointer and return address was. Then when it goes and it returns, it executes the function, it will restore the link register, which is used on PowerPC to return from the stack. So it's loading the link register by R0 from the stack, and then it's restoring other registers, in this case R30 and R31 from the stack, and then it adjusts the stack, and then it branches. Now what we do is, because we control the return address, we actually branch into a known function in ROM-on. And in ROM-on, we have a function, for example, that will, before returning, store something from one register relative to another register. This is what we see here in the STW instruction, first in the second function. This writes R30 into the address of R31 plus address plus offset AB. This is an arbitrary memory write. You guys know that an arbitrary memory write is pretty much like winning, right? So, and because this function also restores the registers and also restores the return address from the stack, we can do the same thing. We can write a second set of values onto the stack, and exactly the same thing is happening, and then we loop into the same function. So we can write whatever we want into memory. This is highly useful. However, we have another problem, which is unfortunately true for PowerPC and for MIPS, therefore for the entire Cisco family, which is cache. Like in 2009, it's really rare that someone has too much cache, but in this case, that's true. So we do have two different caches on PowerPC. We do have an instruction cache and a data cache. So when a buffer overflow happens, the data gets read into the code and gets written somewhere in memory, right? Well, the problem is it actually doesn't get written, because that's the point of a cache. You're not executing the slow-ass memory access. You're keeping it into the cache and then see if the data is actually going to stay, because if the next instruction is going to nuke this buffer, you don't need to write it into memory. Well, that is really bad, because if you return, am I that bad? If you return into that buffer that you just wrote, well, the data isn't there. So you're executing whatever was there before. Bad thing, however, ROM-on is again to the rescue here, because when they load iOS, they also want to turn off the caches, because they're loading code into memory and then like firing it off, right? So they have a function that disables the caches, which we can simply call. And if we put that all together, this is how the current state-of-the-art stable exploitation on iOS looks like. So you have your buffer, and you have your return-oriented cache disable call. So first, you call cache disabling in ROM-on. Then you have an arbitrary memory write, which you use to write the instruction move to counter register stack pointer. So you're moving the stack pointer into a special register. And you write that into the exception handler area, because that's executable. That's on a stable address, because if the exception handlers are not on a stable address, stuff is fucked. And, well, you know where it is, right? So you write it into exception handler. You do the same thing again, and write another instruction called branch to counter register, which essentially, due to the instruction before, means branch to stack pointer. And then you jump there, you execute this data, which essentially means it jumps onto the stack, which you don't need to know where it is because it was in a stack pointer, right? So it jumps onto the stack. Now the problem is this whole stunt actually takes a lot of space, and you don't have much space left for shellcode. So what you do is you use a second stage loader, which is going to go into the router's cache I/O memory, where the packet is going to be located. And it goes there and searches for a magic value within your packet and then copies the packet onto the stack. So you actually have the full IPv4 packet for your shellcode and not just a little bit that you overwrote the stack with. And then you jump there and run your third level code, and then you get this. Now we need to actually get away with it all. So we have reliable code execution, but it doesn't get us anything if we keep running stuff. Remember this Windows 95 scheduler? So we actually need to return from this. So how do we do that? People so far have used techniques like calling the process termination function, like terminate the process they're exploiting. Well, that is relatively nice. However, my research vulnerability is the IP options vulnerability, and the process that parses IP packets is IP input. If I terminate that, the device can only do IP output. This is not highly useful, right? So that's not a good way. The way to actually do it is, remember the stack layout? We have the saved stack pointer in the saved link register. And this is exactly why we're not stuffing all the shellcode into the stack at once, but we use a second stage loader because we need the stack to be intact. So we're actually taking the last intact stack frame and restore all the registers based on that, and then simply return as if nothing happened. This is actually reliable across images. Now the downside of this ROM-on method is actually you need this ROM-on. It's not like you go to the Cisco website and download a copy of it, because the one you're interested in is the oldest one, the one that was shipped first with all the devices. Therefore, it's not there for download, right? So you actually need to physically get routers and dump ROM-on off them and then disassemble them to know where the addresses are. The second problem is you can't fingerprint ROM-on because it's that code. So remotely, you can't actually tell if you're targeting the right ROM-on. You can estimate what's the most likely version, but you can't actually tell exactly before you fire your $150,000 expensive Cisco zero-day against the foreign nation's infrastructure. So this is not perfect. And you still need to know what hardware platform you're dealing with. So alternative techniques will be, well, what if we actually use the same technique with the image instead of the ROM-on? And this is what I'm currently looking on right now. Question, of course, is, well, didn't we just say the image addresses are all random shit? Well, that exactly is the question. Is it all random? So I got myself a new desktop machine with lots of CPU power and RAM, and wrote a very evil Perl script, and then let the Perl script run code similarity analysis on 1,597 iOS images. Disassemblies. Took about a week. And looking for, well, so I need a BLR instruction, right? Like a return from a function. I need the link register to be restored from the stack. I need a write an arbitrary memory write based on a high register value, and that all has to be in the same basic block because it's not supposed to branch somewhere, right? And then you come out with this. You see, it's kind of fucked up, sorry for that. So you see you have 4 different images, and you have the same code sequence, pretty much on the same address. It's slightly pushed down on 2 of the 4 images. Now, if you do that with more images, you will notice a pattern. So why the fuck is it actually on a stable address if it's supposed to be different? Well, there is this thing. They use the GNU compiler tool sets for compiling iOS. And apparently, they actually do alignment within the code, which is nice. So doing that and then comparing the images, I found out that if I have 2 different addresses, so 2 addresses that don't match up in 2 different images, and I compare them with the Cisco Feature Navigator, turns out they're identical. They're just like one minor release apart from each other, but the code is diverted. But then between bigger versions, the code is on the same address again. So this is what you come out with is out of the 1,597 images, 326 had an arbitrary memory write on the same address. This is 20%. This is still not as good as ROM-on. However, this is remotely fingerprintable. You can remotely tell if this is going to work or not. And then the numbers, you see the numbers stay pretty much on the same level. So you're talking 20 to 15% likelihood. I'm going to go ahead and try to figure out what the likelihood is and then get it into groups so you can remotely tell what group an iOS is on and then use that return address. This is still not perfect. You have, what we're talking here is likely code flow. So you have instructions in between that can actually crash your machine depending on the vulnerability you're exploiting and depending on the registers you're controlling. You still have a cache issue. So even if I find the magic one address that's going to work on all the images, I still have that issue of disabling the cache that is solved for ROM-on, but it's not for iOS images. But it can be fingerprinted. So it's the more likely way an attacker will actually use a very expensive Cisco zero-day. Should have not played with the damn animation. So essentially, return address is the hardest problem on iOS. ROM-on is the best way of exploiting it right now. Code similarity looks promising, however, this is actually work in progress. Now, what about shellcode? Now, first of all, shellcode for PowerPC and MIPS is big. On Stack Overflows, it's really easy to overflow the stack and right away hit the heap block boundary the stack is living in with it and destroy the heap, and then the heap manager is going to notice and stuff reboots. I actually wrote a shellcode that will repair the heap within the shellcode. In the shellcode, forget it. So it actually works, but it's like everything but clean and not very useful. Second stage code is pretty much always required, otherwise you're going to crash stuff. However, the I/O memory is not on stable addresses either. So we actually need a way to figure out where I/O memory is reliably to actually make that better. Now, you could write bind shell code. You could actually open a shell, right? That shell is called VTY, Virtual Terminal, on Cisco iOS, and it has been shown before. However, there are 2 different ways to do it. Either you call a function, which you need to find, or you change a data structure, which is not going to be stable, and the data structure is not going to be on the same address all the time. So alternative approaches is modifying the runtime code, modifying Cisco iOS itself in runtime. It's easier because you only need to find one code point instead of a couple of code points that you call. You find one code point that you're going to modify. And what you're going to modify, well, you're going to modify this function that says, is password correct? How do you do that? Well, when you do that manually, you fire up the ilfuck's worst nightmare IDA, and you look for the string password wrong, and you cross-reference it to the code, and then you go to the code and say, okay, here's the password check. Well, you can actually do that in shellcode too. So you actually write a shellcode that disassembles and that finds this unique string. Then it goes through all the memory and disassembles all the instructions, searching for a load immediate followed by an add that loads exactly the address of the string into the register, which is going to be that one function that you're looking for. Then you disassemble backwards until you find the stack setup of the function, and then you just tell this function to return true. If you're interested, this is how it looks like. Other ideas. Newer Cisco routers can run TCL, tickle code. I don't know why let's not even go there. So we could actually write shellcode that loads a tickle script from a remote address, pretty much like a downloader in drive-by exploitation on browsers. And we could actually extend the functionality and then script the router. There has been a very good talk on PH Neutral this year about what you can do with tickle code. I haven't done that yet. Most people have that wet dream of a Cisco iOS sniffer. However, that is not really easy. Routers, as I mentioned, are designed to not parse packets. So if they will parse every single packet and look for passwords flying by or whatever, your email address or stuff, they will actually die on the load. So this is actually not a viable option for implementing in shellcode. However, if you're talking service provider equipment with the lawful interception feature, this is all what the lawful interception feature is about, like matching certain packets and like send them to a third address as well. So if you're exploiting service provider equipment, you can simply call the functions for lawful interception, no matter if they have lawful interception set up or not, because they have it in the image. So thank your government for making shellcodes easier. Same holds true for man in the middle. It's not trivial, almost done. It's not trivial to do, but you can do it. You could actually like send out little information like sequence numbers in TCP, but you can't really play real man in the middle on a router. It would kill it by load. So how do we protect the boxes? I'm over time, but I started 5 minutes later due to your AV guys. How do we protect this? First of all, let's hope. Good luck. It's going to help more than everything else. No, the best prevention actually is to protect the router from receiving traffic. This sounds silly, but it works nice. Nobody is supposed to talk to your router. Everyone is supposed to talk through your router, right? So if anyone is talking to your router, it's better your network manager. Protect your routing protocol updates. If someone can send routing protocol updates, they can fuck with your infrastructure and they can also exploit vulnerabilities that you have never heard before. Don't run stuff on your routers that you don't need to. Don't run HTTP servers, don't run FTP servers, don't run VoIP on your routers. Get a fucking second infrastructure for that. And monitor your service modules. As I said, the service modules are iOS, are not iOS, they're Linux. The service modules are the most likely to be exploited directly in the future. Monitor configuration and crashes. This is the most important thing. Like there are two things you need to monitor. It's like if someone changes your configuration, be that shellcode or a third party, this is bad. You need to know that. So there is a tool called Rancid. It's well established. It's used in service provider networks. It works. Use it. Have your router's configuration monitored. And tell your routers to dump core. You can configure your routers to dump memory when they crash. This is the only way you get solid evidence when the machine comes down. This is the only way you will ever find a zero-day fired against your infrastructure. Nothing else is going to help, no matter what they tell you in the vendor area. Core dumping is very powerful. You can core dump onto a central FTP server. It's even going to make network management easier because you just come in the morning and check the FTP server for incoming files. Awesome. Complaint to Cisco. The problem is nobody patches Cisco IOS because nobody has an idea how to upgrade it without breaking the entire fucking network. Because every time you change the iOS image you're running, your configuration doesn't work anymore and your OSPF comes down. So, complain to Cisco, tell them to do their fucking job and build a decent upgrade line. They should tell you which version is compatible to what version. And if not, they should make it fucking happen. Also, complain to Juniper, complain to Huawei, and complain to pretty much everyone else that ships you fancy boxes for lots of money. Well, let's face it, Juniper has this awesome team of high-ranking names from the security scene. So, and we don't see any advisories. That either means their stuff is perfectly secure, their stuff gets fixed silently and they don't tell anyone, or their stuff isn't even tested by their high-ranking security people. None of that is good news. They should actually come around. Even if Linus Torvalds say fixing security vulnerabilities in kernels is fine without telling anyone, this is not right. Linus is not always right. Cisco is actually doing a really good job in informing their customers about vulnerabilities in their boxes. PCERT is actually a good group. And that was it. Thank you for staying with me.